Thanks, Tamara and Sasha, for the invitation. As you can see, I'm not even a theoretical physicist. I'm a condensed matter physicist. So you can imagine the price I had to pay to the organizers to be invited for a full-time slot talk. Well, and so this is based on one work which has been available on arXiv for 6 months, and another one in preparation with a guy that some of you might have seen, which is Robert Conti, English way of pronouncing it, well known in the integrable systems community, and it's some extension of what I'm presenting alone today, and that will be submitted for a genuine applied math journal. But apart from this, I do not pretend here to be a mathematician, so it's hard, but perhaps I have some results. And when I say this, I guess that everybody of you knows the famous Pauli's quote, he was apparently once asked to give his advice on a paper, and he said, "Not even wrong." So what I'm going to present you today, it's probably true. These are exact results, and perhaps they are even interesting. So let's start with with an appetizer of this tongue twister title. What is Bonnet? Bonnet was a famous French geometer from the 19th century, but probably you know with Gauss through Gauss-Bonnet theorem. So it was the time of the great times of the geometry, differential geometry of surfaces. And so a Bonnet surface is this beast, for instance. This is taken from the cover of Bobenko's webpage, who is also a famous algebra geometer working in Berlin. And the point is that this Bonnet surface permits to answer in a modern language, some question that have been of interest for mathematicians for more than half a century. For instance, the way the usual random real Katz polynomials behaves. So you probably all have seen this problem. You take a random polynomial with random real coefficients. These are centered one, and you can ask for the mean number of 0 with the way it behaves with a degree. And it's a famous result by Mark Katz and a theorem that the average value of the mean number of 0 grows as 1 over square root of 2 pi and a logarithm of a degree of a polynomial. And there is I do not know if you know the simple proof of it. It's essentially because you integrate the average density of 0 in a vicinity of 1, or minus 1, or plus infinity, or minus infinity, because these are the only regions where, if these are of the same order of magnitude, where in the sum you can have compensation. Okay? And if you are a bit more ambitious or completely unconscious, you can ask for more refined quantities. It's generally referred to Katz polynomials, but actually this kind of random series was introduced by much earlier by Hardy and Littlewood, I guess, in 1938. And so you can ask for more refined quantity, the full distribution of a number of zeros of Katz polynomial, say on the interval 0, 1. By symmetry, it's the same thing on minus 1, 0, or 1 plus infinity, or minus infinity, minus 1. So this is an integer valued random variable. You can look at its it's the generating function, and you take generating function, you take a parameter that I call m, between 0 and 1. And one of my claims today, and good luck to prove this, is there exists a scaling function of t, which is log n, logarithm of a degree, but down to 0 up to infinity, given by this, where this object converges with a Pfaffian-like structure if you have a keen eye. And this h there, which depends also parametrically on m there, is the mean curvature of this beast. Okay? And it's also the sole non-negative increasing regular solution of the half-axis of this funny-looking second-order, second-degree differential equation, which is a tau function for Painlevé VI in disguise. And this is the only regular solution with these two Cauchy initial data at the origin. And m appears there. And this 1 over 2 pi is this 1 over 2 pi, actually. And because you can, there is matching down to t equals 0. If you expand this, you will recover, by taking the derivative, exactly this result. So apparently matching takes place for this scaling function. You can interrupt me at any time. You know, when I've not given many talks on this, when I discuss this with my colleagues in my experimental condensed matter lab, I'm trying to say, well, you know, it's like, it's as if I were computing some form factor of Majorana fermions. So they get very excited because in experimental condensed matter physics, the first guy who made an experimental observation of Majorana fermion in topological insulator gets the Nobel Prize. But I say, no, it's not exactly this. So next slide is, not just to pose a comment. So this, when I say it's the only non-negative regular solution, so you have some initial data, and this rewritten as a sum of square, it converts, it grows and converges to a certain limit. And this certain limit, that I denote theta of m, is the average asymptotic curvature of the Bonnet surface. And given by this expression, in which a keen eye as Olex1 will have recognized some expression coming from what is referred to in the literature of the Jimbo cubic of the monodromy invariance. And this recovers, I have to say, independently and by completely different method, for this particular result, a result just obtained by somebody that you heard the name yesterday, thanks to Thomas, about the asymptotic behavior of this full generating function by, found by Mikhail Poplavsky and Gregory Scher, that some of you have probably also seen. He has been hanging around as a physicist in the random matrix theory conference for some years. And so it's the same result up to this change of this correspondence. So this is the way the two scaling variables speaks to each other. And they had this result by completely different means, and 3 months before me, but not the Painlevé function I was discussing at. Actually, we were in competition on this. And both of us, anyhow, are answering a famous question raised in a paper by Dembo, Lee, Shao, and a fourth guy I've forgotten, in a 2002 article of the AMS. And the title was Random Polynomials Having Few or No Real Zeros. And they showed that this, so the way you can obtain the probability that a random Cax polynomial has no real zero on the interval 0, 1 is by taking the limit of this generating function. And they had some, they showed there that this limit existed, and it was related to a first passage property of a certain Gaussian stationary process, and had some bounds for the exponent. So to summarize, both Gregory, Mikhail, and I have the exact value for this exponent. And the funny thing, and you could say, okay, this guy has a paper with Robert Kant. Robert Kant is well known for being the guardian of the temple of the historical, classical Painlevé literature, French authors from the end of the 19th century, beginning of the 20th. But this is modern application. And what is useful with Bonnet surface is that this is not only the average extrinsic mean curvature, but it's Gauss intrinsic curvature. So if I have a surface, a two-dimensional surface immersed in three-dimensional Euclidean space, I have two kinds of curvature, the average curvature, extrinsic, depending on the embedding, and Gauss curvature, which is really completely intrinsic, independent from any conformal reparametrization. So, and the 316 exponent is the top there, the curvature of this exponent there, essentially. So, next slide. I mentioned that the difference with Poplavsky and Scher work is that I have not only the asymptotic behavior, but the full scaling function characterization, and it's given by a certain Painlevé VI transcendent. And you do one way of doing the identification is with this Bonnet curvature mean function, ODE, and these are the monodromy exponents, or for those who prefer the alpha-beta traditional notation, it's 1/8, minus 1/8, 0, 1/2, up to, of course, permutation of a monodromy exponent. So some very simple monodromy exponents. Halfway, what of my main claim here, and one of my main interests to work on this topic, is that this gives actually for 4 different models of interest for statistical mechanics, a universal scaling function that I dare to call it a la Tracy-Widom. Sorry, Craig, especially because you don't have yet seen the end of the talk, so I do not know if I deserve this name. And also, even though also it's closer in spirit to Jimbo Miwa Morris Sato characterization of Godin eta distribution for the sine kernel, Painlevé V. But it's shorter to refer to as Tracy-Widom, I would say, among other reasons. So, sorry. So just about the monodromy exponents, it's halfway between 2 other famous Painlevé VI that you encounter in the literature when you end up with those kind of beasts. Okay, you check in the literature if those simple monodromy exponents have appeared somewhere. So if everything is 0, it's Picard solution. The only explicit solution for any the only case where you can write down up to Okamoto transformation the explicit solution, up to Okamoto transformation, so that's true. The only transcendental case. And it's also related from some tortuous quadratic transformation to famous Painlevé VI that appeared in a completely different context, which is Manin's Painlevé VI. There was a passionate discussion yesterday at the evening that made me miss the cheese banquet and the dessert, because I had to check that there is a typo in Manin's paper, actually, I've been told, but it's still true. I've checked and missed the dessert. At the point, so there was a fight I mentioned with Gregory, but we were off target because all this business about Cox polynomials and stuff like this, we are just solving for probably the 1,000 times the 2-dimensional static planar Ising model with some transformation. It's not just a conjecture. I have the exact microscopic correspondence related to the interaction and energy in direct and dual space. And this 3/16, so if you have to remember something, is that the 3/16, this exponent, is just the half sum of a Fisher-Wu and Onsager-Young magnetization exponent for the two-dimensional Ising model. 3/16 is indeed the half sum of 1/4 plus 1/8. Okay? And the reason for all this is, as you can guess, that there is a Pfaffian structure and with an integrable kernel, and I'm going to compute all kinds of random determinants and eventually relate this to Painlevé VI. But, so I said it was an appetizer. I do not know if it's easy to swallow. And I will start with the first course, which is a normal introduction, which is perhaps more interesting for you, because it will show you the motivations that, as a number crunching guy, led me to commit myself to this for several years. So it's an old applied problem I was looking at, the persistence. It's another name in applied probabilities, the first passage properties of a random process. And the basic question is, you have a fluctuating quantity, and you ask a question which looks dull, so you want to know for how long your fluctuating quantity has been always, that's the important keyword, above its average value that you put to 0, because the usual playground is to consider, to make things simple, a Gaussian stationary process, because a priori you know the joint clause of any marginal times at any number. And it's because it's determined by its two-time correlator, which is a translationally invariant function. So you have this, you know the joint, an arbitrary joint marginal, and you ask this question, the no-crossing probability at 0 level up to fixed time t. So if I were to represent this, I have a stationary process, and a random one. And okay, I start off, this is time, and I want the distribution, the tail distribution, this is 0, of this interval, to have always been above or below the 0 level. It looks simple. It's a question that people at Bell Labs asked during World War II when they were trying to develop the radar, so it was interesting if you... It's a question about a signal over noise ratio. You want to put a threshold to be sure that you measure something. And if it's a plane approaching to bomb you, that can be of some interest. And you can intuitively, if this two-time correlation function decays exponentially fast, you expect that you will decorrelate also fast enough for this length of time t, and this beast will decay exponentially, and theta is the decay rate of this quantity. Well, that looks simple to state. To the best of my knowledge, in a recent review article by Wenbo and Lee, Wenbo Lee and Kim and Shao, that were two of the people involved in the paper by, with Denbo I mentioned 5 minutes ago. There are just 7 processes for which the decay rate is known exactly, and even less where you can compute exactly and prove the first passage probability at time t, which is this is the tail p0 of t, p0 of t is the tail probability distribution, so minus the first derivative is the density of 0 crossing at time t, okay? And you just basically have 2 results. You have a bound, no, you have one result which is a theorem by Slepians. If your correlation function is a pure exponential, then your process is essentially a time change of Brownian motion, and by one of three Levy's arc-sine law, you will have the exponential decay of this quantity, with precisely the decay of the autocorrelation function exponent. Otherwise, you just have bounds. What people do generally, okay, and this is the way Dembo proceeded, they had a certain non-Markovian correlator. When I say it's non-Markovian, it's when it's not a pure function. You keep the memory forever. And they bounded their correlator, and this way, using a corollary of Slepian's theorem, they have bounds on their exponent. And you know the way physicists proceed, okay, this is what is known from mathematicians. They cannot do better, so we are going to complicate the problem so that everybody can work in his own field, and for sure there will be no intersection. So it's a question that resurfaced in the 90s in statistical mechanics through the work of essentially two groups led by Bernard Derrida on one side and Satya Mayumdar on the others. It's a question about non-equilibrium statistical physics, but a simple question. You want to know how a system, a stochastic system is resilient to its disordered initial condition when local spatial order develops. So I put this here. What happens, for instance, this is snapshots taken from my thesis, so I should have copyright on this image, but I'm not even sure. You take the two-dimensional Ising model, ferromagnetic, at 0 temperature, you let it evolve, but you start it from a completely random initial condition, where each spin is plus or minus 1, and you take whatever dynamic. So what's going to happen? So in front of a physicist audience, everybody knows this, but it's my duty to explain this to you. We try to reduce the energy cost, so you will begin by eliminate domains of opposite spins. So the spins will locally align, and by eliminating defects. And you will have growing domains with, in these situations, growing domain as square root of time. I think for a two-dimensional system, it's rigorously proved, perhaps in 2 cases. You can do this in 1D also, and this, you have Brownian motion, it's better. And people noticed it was also motivations coming from pure probability theory from some interacting particle system. So people ask a natural question in this context with this picture. Okay, you see growing domains, but they are growing quite slowly. And you can see that, for instance, if I take a spin deeply buried in, it's less likely to flip, to change its orientation soon, because if it's going to be swept over by a neighboring domain walls, well, these domain walls has to move, and so it will take some time. So people realize this way through this. So there are two definitions: geometric ones. One, which is a fraction of spins which have never flipped up to time t, that have always maintained their initial opinion. Yes, Ricardo?
Let me make a physicist question. Is it Glauber or Glauber?
It's Glauber.
Oh.
Okay. I wrote it here. And people realize that it's decaying with an exponent. But I called theta for a good reason, and they call this persistent exponent. Perhaps a better wording will be resilience exponent, because it's the resilience of a system to its initial condition. And people, of course, you have an exponent, you are a statistical physicist, you want to compute exponents. That's the only thing that matters. You don't ask about proving the existence. So there are two essentially two results about this during this flurry of works in the physical literature. You can take the simplest model, which is the diffusion equation, starting from white noise Gaussian initial condition. Okay, you have to modify the noise if you render this proper, but this has been done by Dembo later. And you just can ask, so you have it's a sum of Gaussian process, and you just can ask about you can consider the sign of a diffusing random field in all dimensions, and ask for the probability that this sign has always been the same, either +1 or -1. And so it's the diffusion equation, and you have a non-trivial exponent in simple diffusion. Okay, this is the popular science way of putting it. But the reason is simply, if you compute the correlator, the two-time correlation function of this object, it's a Gaussian process, and you do what is called in the probability literature the Lamperti transformation, which corresponds just here to looking at the process on a logarithmic stationary timescale t, which is logarithm of t, which is the same t that I was referring to in my introduction. It's a stationary Gaussian process. So it's a stationary Gaussian process with a non-Markovian correlator, meaning that a correlator that is not a pure exponential, and you expect a non-trivial decay rate exponent. And this is what happened. In particular, in two space dimensions, the theta tilde is equal to something that seems quite close numerically, at least, to 316. I do not know if you play with fractions, but 0.1817 is actually the closest fraction you can imagine out in a numerological behavior is 316. And the corresponding correlator is simple. It's the sec function divided by 2, and I remind you that sec is the inverse of cosine, okay? The interesting point is that it was later realized both in the mathematical, physical, and mathematical physical literature at independent times and nearly simultaneously, and of course with different techniques, that the very same Gaussian process with this correlator also describes, in appropriate asymptotic limits, the number of real roots of random real Kac polynomials or the eigenvalues of truncated random orthogonal matrices. So now perhaps if you have not forgotten what I said at the beginning, you can see the connection. So I come from here, from this persistent business, and I notice that for this correlator, you could apply methods developed by Craig and Harold. And this is the way I get the Painlevé VI transcendent at the beginning. But to do this, actually, I shall mention the other climax in the early 90s literature. So it's a genuine and a sincere tour de force by Derrida, Hakim, and Pasquier. I mentioned that Derrida and Pasquier were two former PhD students of Gaudin, so it's not amazing, perhaps. And so they have obtained an exact expression for a more general model, which is in one dimension, zero temperature dynamics, Potts model, which is Q-state Potts model, but an expression valid at all times. But extracting this exponent was really very hard. I think they spent 1 year working at free to have this. You have all kind of Toplitz's determinant manipulation, Sego's theorem in it. And when you look in detail at details in the proof, so the natural question is not just for Q-valued Potts spin, but just for Q equal to Ising spins. And you cannot access the result directly. You have to make a subtle limiting procedure and to obtain 3/8. And the crucial point, the crucial observation, first I'm going to draw this. Is that for a related model in another geometry, they managed to evidence a Pfaffian structure for the meeting probabilities of random walks with which they are computing all this business. And it's not the full Ising chain, but you have to consider a half space Ising chain. So this is space, this is time, and you just consider the probability that this spin as the origin has never also always kept the same initial opinion since between two arbitrary time, T1 and T2. And the reason why you can do this, and only in this particular geometry, is that at 0 temperature, it's a correspondence with a certain stochastic process, which has been introduced in the 70s. It's the voter model. The voter model is the simplest caricature of the way people vote, but given the way people have voted in recent times, you can say it's not even a caricature. You have two opinions, and you just take the opinion of one of your neighbors chosen at random. And if you do this, you realize that you will just execute a random walk down to the initial condition. And if you are to compare the opinion that you had at one instant of time and at a second instant of time, so you have a path of opinion, the successive opinion you had in the path, and you have to decide whether those two random walks paths have crossed or not. And so there is some intersection probabilities of random walks, which is given by this in terms of a propagator for a simple random walk on this half space chain with reflecting boundary condition. And this is the scaling form. And the peculiarity of the half space Ising chain is that the right side and the left side evolves independently in decoupled fashion. So the persistent exponent for the spin at the origin of the half space Ising chain is just 1/2. So 1/2 of 3/8 is 3/16. So I have 3/16 and a Pfaffian structure, and this turns out incorrect variable to be related to an integrable kernel. But when you still dug deep in the proof of Derrida, you write something that is not used to write and that you hardly see in some scientific papers, some kind of regret. This probably means that there are simplest way of rewriting our expression where all the cases can be treated in the same manner. Unfortunately, we did not find these simpler expressions. And so I already unveiled part of the truth. So the half space persistent exponent for the Ising chain and the persistent exponent or decay rate corresponding to random polynomials. So you had this as an exact result, and at those time for 20 years, you had this. The first question you can ask, so you have two model systems. One is 1D, one is 2D. You have dynamics. You have dynamics on top of both, and they are not obviously related. And so I was after this for some time, and I was quite pissed off when I saw last summer this article where by Mikhail and Gregory. So Mikhail is a mathematician, Gregory is a physicist, and it's published in Physical Review Letter, so I do not know how you as mathematician you will consider this. It's a genuine question. And so they show this, and they have this identity actually as process, as probability processes. So I was after this, and my hope So I had vague indications at the time of Painlevé VI lurking in the background, and my hope was that this could allow to rederive this result somehow. Okay? So this is true, and there are 5 decisive critical steps, and there are 2 steps that where there are gaps in the proof. I said earlier that I'm not a mathematician, but for sure I can see that there are something that should be true, but I cannot prove them, and it's not my duty to prove them, I would say. So it's going to be a bit technical for the moment, because I show you how you can put all this computation in the framework streamlined by Craig and Harold. And this is the architecture of a proof. This is a picture taken from Michael and Greg paper. So at the heart of all those processes, you have a Gaussian stationary process with this sec kernel. So it's related to 4 other Gaussian processes: CATS polynomials, truncated random orthogonal matrices, the diffusion equation in 2 dimensions with random initial condition, and as I just mentioned, the semi-infinite Ising chain at 0 temperature with Glauber dynamics, or semi-infinite or half space Ising chain. And when I received this paper, I scribbled this, and I'm going to attack it this way, okay? And scribble this with Painlevé VI around. So what I do, and the difference with what I do, is that I show, I attack this way, it's equivalent, I show that these 2 processes coincide, and I have a full scaling function of both. And actually the results I presented you at the beginning were using their connection, meaning it's the same scaling function, so I'm using the connection they have there. And how I do this? Elementary methods, I would say. I don't have any representation theory, no Riemann-Hilbert, no conformal theory, no isomonodromy, just some commitment, I would say, yeah, again, stamina, resilience, no algebraic geometry, essentially by now classical Tracy-Widom freedom determinant operations, and old school Painlevé VI literature, because Robert Comte was my first nearest neighbor in Saclay, and I had to find somebody to talk with. So I shall mention also that this Painlevé VI Bonnet correspondence, in my opinion, so I might be wrong, gives the only explanation on the market why experimentally for KPZ you observe curvature dependent universal asymptotic height distribution. You keep the memory of the initial condition. You keep the memory of the initial curvature. Because the Bonnet-Painlevé VI correspondence is working actually for the generic Painlevé VI. So if you do the usual confluence down to Painlevé II, which is the Painlevé II transcendent involved in Tracy-Widom usual distribution, you should also keep the curvature interpretation. There is, as far as I know, there is no other explanation on the market. I leave this open for discussion. How many time do I have left? 10 minutes? Okay. So, the literature I use is quite short. So my base camp is Derrida, Hakim, Pasquier. Then I use 2 magnificent papers by Craig and Harold, where when I say magnificent V, because it's really clear. You can do, you have algorithm, you can do computation. And at the time, when reading mathematical papers, for instance, this one, I had the feeling to have to decipher Klingon, you know, this language used in Star Trek. There is another paper by which makes the Bonnet-Painlevé VI correspondence by Bobenko, which is published in the Creils journal. And the last paper I use is a recent one, an electronic journal of probability by Matsumoto Shirai, where they identify the zeros of the Kax polynomial with a Pfaffian point process. Okay? Plus approximately over 200 references in the JState Phys paper I'm going to submit. So the idea to do this, and this is the first gap in the proof. So I'm computing the, and this is the move that was missing in Derrida-Hakim-Pasquier. I'm computing not for the semi-infinite Potts chain, but I'm switching directly from Q-state Potts spin to Ising spins with an on an arbitrarily magnetized half-space chain, because if you have Q-state Potts spin there, you can as well group one color chosen at probability 1 over Q and to say it's plus, and the Q minus 1 over 1 as minus. And so this it's the reason for this identification, and I start from the very beginning in logarithmic stationary time scale, and there is some subtle sum rule in this probability, so which means that one probability, this one P0 plus, which is the probability that when looking at the stationary logarithmic time scale, the probability that this spin has not has always been in the plus state for a length of time t. And the point is this probability, thanks to this algebraic rewriting there, is related to the sec kernel through this intersection probability. So there is an arctangent. You plug in the expression for the arctangent, and you have this. So it's just a sine integral of the correlation kernel. In more invariant probabilistic term, and that makes the link with between the 2D Brownian motion, which is the diffusing random field, and the 1D process. This is just the conformal invariance of the exit distribution of two-dimensional Brownian motion. So I take Brownian motion starting at the center of the origin, and I am asking where it's going to exit the unit circle. Well, uniformly distributed on the circle, and and the basic building block of the Pfaffian expression are actually a fraction of the of a quadrant of the unit circle. And to compute the probability, the persistence probability, I'm doing some stereographic projection on this. So this amounts to this. I'm going to speed up. So you have freedom determinant, and the advantage of this reformulation, this is is that these two probabilities that initially takes this value 1 plus or minus m divided by 2, Bernoulli random initial condition. When you do all the transcription, they are just the half sum of the even and odd part of a freedom determinant. Okay. So in a certain sense, I'm in the right basis for this quantity, and I can resum the persistence probability with the freedom determinant. And the full persistence probability, the summing over the two possible states, and I'm using your notation, Craig, so don't be confused, please, is just the integral over the resolvent for the sec kernel at coincident and non-coincident points. speed up things. So it was not given in the article of Derrida, but you have this, and essentially what I'm doing is what impresses me more in what they have done is that they have done exactly in a contemporary way of your article, the same Pfaffian manipulation. So they have an easy part, which is the square root of a usual freedom determinant, and they have this amplitude, which involves some rank 2 projection operator, and you can rewrite this. And you realize at the end that it's an intrinsic computation that just rely on the Pfaffian structure of persistence priority, and as a bonus, the M parameter, so the initial magnetization you started with, is really the generating function parameter of your sec kernel. So, and it's exactly, but for another different kernel, the computation in a different language made by Gaudin in 1961, when he first expressed the spacing distribution in the orthogonal ensemble in the bulk. In a modern language by Forrester, so it's the spacing distribution for the sine kernel. Here I don't have sine, I have sec. But sec sounds like sand, but it's Painlevé 6 instead of Painlevé 5, I would say. So this I can skip. So I just said it was an intrinsic computation, valid for any even difference kernel on symmetric interval. But now I have to do the real computation. So the sec kernel, if I rewrite it this way, so I have this, I multiply by a sine of this difference at the numerator and the denominator, and I'm using this identity, so it's exponential Christoffel-Darboux-like form. I can apply this method, and actually that was the first idea I had to embark on this, because I noticed this trick, and I remember that for the finite n sine kernel, which means before taking the n to infinity limits, so this is also called the circular unitary ensemble for finite matrix size n, you have this kernel. So formally, it's the same thing for n equal +1/2 or -1/2. It's not only formal, but it's true, because the Painlevé 6 characterization of this gap probability, the monodromy parameters are n squared. Two of them are n squared, one is 1, one is 0, and it goes through, meaning that you have continuity in the monodromy parameters of your tau function. So, having noticed the Christoffel-Darboux identity, you write down the usual system of differential equation. The first relationship is due to Gaudin, never published, and Pasquier, I went to see Pasquier, he's still in Gaudin's office. Yeah, I can find the letter that Meta is referring to, where he proves the conjecture that Dyson had. And, so this is universal, and if you do the elimination, so this is the H, I absorbed the T/2, G, so it's a single function of a resolvent at an opposite point. You have this beautiful symmetric equation, okay? And you can do the differential elimination of J, and you end up with the equation I wrote at the beginning. So you have this, and you can, so the initial conditions are given by the Neumann expansion of a resolvent. And what I'm saying, I've not yet proved it. It's the equivalent of the Hastings-MacLeod solution for Painlevé 2 that appears in the Tracy-Widom distribution. That is that there should just exist a regular solution on the full half-space real axis of this equation. And this is the exact analog through this formula for this Painlevé 6 of the G beta E distribution, but it's not it's not the cumulative, it's the complementary distribution function. So this is a persistent probability, E1, empty spacing, and you have exactly the same characterization. And you can also do, I'm speeding up, the usual birational transformation between Hamiltonian of Painlevé VI evaluated on this equation of motion and the genuine Painlevé VI ordinary differential equation, and you end up with the Painlevé VI I showed, which is a bit bulky, and I put, it's another choice, I put the exponent 1/8 and 3/8, just to recall the exponents I was trying to compute. So up to permutation in the monodromy exponent. How did I do this? And this is the way Robert Comte came into the play. So how many minutes left? 2?
-1, I would
okay,
say.
-1. Well, how did I do this? I had this, and so I knock at my first neighbor, and just trying in the last minute to pay justice to what he has done and how he has helped me. So for those who have not met him, Robert is not Sofia Kovalevskaya, neither Poincaré, neither Fuchs, neither Painlevé. It's here, and it's to pay justice to the way he writes paper, meaning that it's so cryptic that it has to be translated in Cyrillic for a better understanding. Sasha, sorry for putting it this way. And actually, I showed this equation, and he jumped out of his chair and turned to his shelf and dug from it 1867 paper, Journal de l'École Impériale Polytechnique. It was a time where in France we had an emperor. Now we have even better. We have Jupiter, Macron, and by Monsieur Ossian Bonnet, the 150 pages paper, when you can find buried somewhere, signed Gordon. And he had all the reasons to know this, because just 2 years before, he used this correspondence found actually by Bobenko for certain condition to Painlevé to write the best lax pair for Painlevé VI, because I'm going to curse to conclude this talk. Jimbo and Miwa made a very bad choice for the monodromy exponent. So thank you. Actually, just to mention, there are many other non-trivial distributions that you can find. For instance, you look at the imaginary distribution of Brownian motion, and this is related to Painlevé III signed Gordon. Thank you.
Thank you.